Now the last piece of this is this idea of something called even, odd. The labeling of these functions as even and odd. It turns out sine is an odd function, cosine is an even function, tangent is an odd function. Let's review a little bit where that terminology comes from and sort of convince ourselves this is actually correct. This is not going to be a proof of this, but this is a sort of a motivation for us to why this nomenclature is correct, this terminology is correct. If you remember from your glory days back in the basic algebra course, you probably talked about, if you had a good course, you talked about even and odd functions. Now, consider this the function y equals x squared. Now, if you choose any point on that parabola, if I choose that point, and then draw a line to the y-axis, and continue through the y-axis the same distance, then within the limits of my terribly drawn picture here, is it clear you will be back on the curve no matter where you start? Draw a line to the axis, to the y-axis, through the y-axis, you will be back on the curve. If this distance is the same as that distance, then these 2 points will lie on the curve. If this distance equals that distance, and no matter where you start, draw to the y-axis, go through, this is through the y-axis, then you'll be back on the curve. All right? The x squared function has that property. There are other functions that have that property. The absolute value function has that property. There are others that have that property. But the point is this. Any function that has this property behaves in that manner. It behaves like the x squared function. Any function that is the reflection of itself across the y-axis is called an even function. It's just a terminology that we inherit from the fact that this is x squared. It turns out x to the fourth has this property. X to the sixth has this property. X raised to any even integer power has this property. And so any function that has that property is called an even function. One of these functions has that property. Well, if I choose a point on the sine curve and go to the x-axis and go the same distance, I'm not back on the sine curve. Sine does not have that property. It is not the reflection of itself across the y-axis. But we can see, if you choose a point on the cosine curve, draw a segment to the y-axis, continue through the y-axis, that same distance, you'll be back on the curve within the limits of my badly drawn picture. And so this point is the reflection of this point across the y-axis. This trough point is the reflection of that trough point. This curve is the mirror, no matter where we start. This point, go to the axis, through the axis, you're back on the curve. And so this curve exhibits that same symmetry that this curve does. It is the reflection of itself. If you could fold this board across this axis, this would fold precisely onto itself and vice versa, just as this one would. Cosine is an even function. Now, any even function says this. Any even function, the negative vanishes. It is the case that if I take 3 and negative 3, if I take the square function of negative 3 and the square function of 3, the square function of 3 and the square function of negative 3 are equal. The square function of negative 3 is the square of positive 3. This negative sign vanishes just like this negative sign vanishes. The square function has this property. Any function with this property is squared. It's a square function. If you can remember that cosine behaves like the square function, when you square, the negative vanishes. Cosine is an even function. It behaves like a square function. The negative sign vanishes. Now, let's consider this other scenario. Look at the cube function. The cube function is rather a bit more complicated. Choose any point that lies on the cube function. Draw a line segment to the origin. continue through the origin the same distance. Then within the limits of my poorly drawn picture, you will be back on the curve. And is it clear? It doesn't matter where you start. If I start here, go to the origin and through the origin, that same distance, you'll be back on the curve. No matter where you start, you'll be back on the curve. X to the third has this property, x to the fifth, x to the seventh, x raised to any odd integer power has this property. And so we call this, any function that behaves this type of symmetry is called an odd function. Well, I claim that sine exhibits that function, that property. If I choose a point on the sine curve, go to the origin, through the origin the same distance, within the limits of my badly drawn picture, if this were an accurate picture, it would be perfect, you're back on the curve again. If I start here, go to the origin, through the origin, you're back on the curve. If I start at this point, go to the origin, through the origin, you're back on the curve. So sine, this is the function y equals sine of theta, or sine of x. The sine curve exhibits the same symmetry that the x to the third curve exhibits. Any function that exhibits that behavior is called an odd function. And so we can say that sine of negative theta is negative sine of theta. And here's where that comes into play. What is the cube function of negative 2? Is that equal to the cube function of 2? Well, no, this is negative 8. This is positive 8. Those are not equal. What do you need to do to make this thing equal? If you make this negative and make that negative, then yes, they are now equal. And so cube of negative 2 is equal to the negative cube of 2. That's long and wordy. The net result is this is the property that odd functions exhibit. Since the sine function has the same symmetry model as the cube function, sine is an odd function. And when you cube an odd number, the negative is retained. When you cube a negative, the negative is retained. When you cube a negative, the negative is retained. Odd, when you raise to an odd power, negative sign, the negative is retained. So that might help you remember that. Now the question is, which of these symmetries does tangent, if any, which of these symmetries does tangent exhibit? Well, it is clearly not the reflection of itself across the y-axis, because this point does not reflect to itself. If we tried this green symmetry, choose this point, go to the axis, go through the same distance, we're not back on the curve again. It is not an even function. However, it does exhibit this blue behavior. If you start on the curve, go to the axis, go through the axis, same distance, you're back on the curve. No matter where you start, you have that same behavior. If I start here, go to the axis, go through the axis, you're back on the curve. And so tangent is an odd function, and that's why tangent of negative theta, the negative sign is retained, because odd negative signs are retained. And so that's why tangent of negative theta is negative tangent of theta. That's where this even odd nomenclature comes from. That's not a big deal, but if you're in a course somewhere and some instructor starts to say sine is an even function or sine is an odd function and uses this property, you know what they're talking about. When we say cosine is an even function, that's where cosine negative theta equals cosine theta comes from. That can help in the memory, because for an even function, the negative gets squared away. For an odd function, the negative does not get squared away. An odd function, the negative does not get squared away. Another way to help is this. Cosine is even, sine is odd. But when you divide an even by an odd, your answer is still, when you divide an even by an odd, your answer is still an odd number. And so that behavior is the same with tangent. So that's where we get the nomenclature even odd, and that's where we get our negative angle, negative argument properties.